Hello everyone, in this video we are continuing class 11 chemistry chapter 4 chemical bonding and molecular structure. In this video we are going to learn resonance structures of molecules. We have already learned bond parameters, that is characteristics of bonds. Magnitude of these characteristics or parameters can be calculated theoretically or determined experimentally. Theoretically, we calculate it and practically we measure it. But in many cases, it has been observed that these two values, that is values obtained experimentally, do not coincide with values which are expected theoretically, that is obtained by calculation. So, in order to explain the structure of these or such molecules, the concept of resonance structure is used. In order to understand that, we will take two examples. But before we go into the details of the video, please do not skip the video. Watch it completely so that you get all points clear. Then it becomes easy for you to answer what is discussed in this video and also apply what you have understood from this video to other questions which may be asked based on this. I am Anandavelli from Guidance Education channel. I welcome you all to this new video from Guidance Education channel. Come, let us start the class. The first example is ozone molecule. Ozone molecule is O3. It has 3 oxygen atoms in one molecule. We have already discussed in the previous videos how to represent ozone molecule. There are 3 oxygen atoms, there is one double bond and one single bond. In case you have forgotten, I will provide the diagram. Ozone molecule is represented here in 3 different ways. I will explain. Let us mark these 3 diagrams as structure 1, 2 and 3. Let us number the atoms in the molecule as 1, 2 and 3. In the first representation, you find the double bond between atom number 1 and 3. So, the first oxygen atom has one lone pair of electrons. And the oxygen atom marked 3 will have 2 lone pairs. The second atom is bonded to the first oxygen atom by a single bond. So, that second atom now has 3 lone pairs. O double bond O, the bond length is expected as, that is theoretically as 121 picometer. O single bond O is equal to 148 picometer. These two values are theoretical values. That is, this is the expected bond length magnitude. The position of the double bond can be between 1 and 3 as is shown in figure number 1 or maybe between atom number 1 and 2 as is shown in figure number 2. So, there are 2 possible representations. This molecule cannot be represented by a single Lewis structure. This molecule can be represented in more than one structure. So, there is a difficulty in representing this molecule. Hence, the concept of resonance is used. These 2 structures are called canonical structures. The double-headed arrow between these 2 canonical structures represent resonance. According to the concept of resonance, whenever a single Lewis structure cannot explain the structure of a molecule, then a number of similar structures with similar energy, position of nuclei, with similar bonding and non-bonding pairs of electrons are taken as canonical structures. So, by the principle of resonance, structure 1 and 2 are canonical structures of molecule ozone. Okay, so theoretically the bond lengths for the double bond and single bond are found to be different. But when these bond lengths were experimentally determined, the two bond lengths were same. That is, the double bond as well as the single bond had the same bond length, equal to 128 picometer. Slightly bigger than the bond length expected for the double bond and slightly smaller than the bond length expected for the single bond. The magnitude is somewhere between these two values. Though the experimentally obtained value is not perfectly the average value, it is called the averaged value. So remember that. So the structure of the molecule considering this experimentally obtained value of bond length is represented under structure 3. There you will find both bonds are partially shown as possessing double bonds. One solid line and one dotted line suggests that it is partial double bond. This structure is called resonance hybrid. The three lines shown in yellow color means they are congruous. That is, these two canonical forms are congruous with the resonance hybrid. The molecule really exists as a resonance hybrid. That is third structure. It does not exist as structure number 1 or structure number 2. Please note this point. It exists as structure number 3. That is resonance hybrid. I will mark the bond length in the resonance hybrid as 128 picometer. Both bonds have the same length. I hope it is clear. Now, why should this molecule exist as a resonance hybrid and not as any one of the canonical forms? The reason is the resonance hybrid has a lower energy level when compared with the canonical forms. So the energy of the resonance hybrid, I will mark it as RH, is lower than the energy of the canonical forms. And we know less the energy, more the stability. So the resonance hybrid is more stable than the canonical forms. That is why it is existing as resonance hybrid. The first reason is stability of resonance hybrid. I have used the short form RH for my convenience. Better write it fully. And the second one is the bond parameters are averaged. I have already explained what we mean by averaged value. Here we have considered the bond parameter bond length. The experimentally determined value is something in between the expected values. That is what we mean by averaged value. We may conclude that the molecule exists as resonance hybrid for stability. Now let us see a few misconceptions regarding resonance. One misconception is that the form exists as canonical forms. Another misconception is that for a fraction of a time it exists as, say, structure number 1, and for the other fraction of a time it exists as structure number 2. The third misconception is that there is an equilibrium between these two forms. All these three concepts are misconceptions. Such a thing does not happen. Really, the molecule exists as the resonance hybrid. That is, in the case of ozone, I have shown that structure 3. Now we will take another example, the carbonate ion. Ozone is a molecule. Carbonate is an ion with 2 negative charges. CO3, 2 minus. In all there are 4 atoms, 1 carbon atom and 3 oxygen atoms with 2 negative charges in excess for the whole ion. I have provided the diagram there. I have shown 3 pictures. I have given the three possible canonical forms of carbonate ion. Structure 1, structure 2 and structure 3. In all the three different forms you find one of the oxygen atom bears double bond, and the position of the double bond is different in all the three representations of the carbonate ion. The oxygen atom bearing the double bond has two lone pairs, and the other two oxygen atoms bearing single bond have three lone pairs each in all the three canonical forms, and the double-headed arrows represent the canonical forms. So it is expected that the double bonds are shorter than the single bonds. So in the diagram, the double bonds are shown shorter than the single bond. But when it is measured, in the carbonate ion, all the three bonds have the same length. So there are no three forms. There is only one form, and it has a bond length in between the bond length for the double bond and the single bond. So it suggests that all the three bonds have partial double bond. So the molecule does not exist in any of the canonical forms. It exists as a hybrid of these three canonical forms. In all the three forms, the oxygen atom bearing the single bond will have one negative charge each, so that the ion has two negative charges. So it exists as the resonance hybrid. It is very easy to draw the carbon atom in the center and three oxygen atoms around it, and each bond has partial double bond nature. Any of the two oxygen atoms among the three will bear the negative charge. So I have not shown the lone pairs. I hope the video was of use to you. We will meet in the next video with another important topic like this. Till then, bye. Take care.